Okay, so let's talk about the cars and goats and choices and switches. Let's make a deal. The player picks a door. The host opens another door, shows the goat, and asks the player whether the player wants to change their choice. For example, the player started by saying, I think the car is behind the door 2. Now, should she go like, wait a moment, no, I think that the car is behind the door 1. Should she switch? Does it matter? Should she stick to her choice? Let's use probability to figure it out. So originally, it's equally likely that the car is behind any of the doors. So her probability of picking a car is 1/3 no matter which door she picks. She picks the door number 2, with probability 1/3, the car is there. So now what happens when the host opens the door with a goat? Two possibilities: either she picks the door with a car or she picks the door with a goat. If she picks the door with a car, and that happens with probability 1/3, then by switching she would switch from the car to a goat. Not so good. And this would happen with probability 1/3. But if she originally picked a door with a goat, and there are 2 goats and 1 car, so there is a 2/3 probability that she picked a door with a goat, then she would switch to a car. So now you see that switching looks a lot better, because even though originally all the choices were the same, now if she switches, she gets a car with 2/3 probability, and if she doesn't, she only gets it with 1/3 probability. This is quite counterintuitive, because you may say, wait a moment, why should it matter? The cars didn't move, the goat didn't move, nothing moved. But what happened is that she got an additional information. The host knew which of the 2 doors that she didn't choose had a goat. And now she also knows which of the 2 doors that she didn't choose has a goat. So this changes from uniform probability to something different for her. And this additional information lets her make a better decision. So how would we talk about a situation like that, when we had probability 1/3, nothing had changed in sample space, but suddenly we have a different probability? And we do it by using the notion of conditional probability. And what it does is it tells us that whatever the probability of event A was before, now we know that some other event B occurred, and that may affect what the probability of event A is for us with this new information. So, for example, suppose the weather forecast says that probability of rain is 40%. If you look outside and you see that it's sunny, you say, no, 40% is probably not gonna rain, look, it's sunny. If you look outside and see a big black cloud above you, say, wait a moment, okay, I see a big black cloud, so I think it may rain after all. 40% is not such a small probability. What happened in that reasoning is that conditional on it being sunny, the probability that it will rain went down. Conditional on it being cloudy, having a big black cloud above you, the probability of rain went up. So even though your probability of rain by itself is still 40%, conditional on a cloud it's more, and conditional on sunny it's less. And similarly, in the Monty puzzle, probability of a car behind any door, let's say door 2, is 1/3, but probability of a car behind the door 2 conditional on the host showing the goat behind the door 3 is 2/3. And by the way, it's not just conditional on there being a goat behind the door 3. It's also conditional on the host choosing to tell you that there is a goat. So how do we calculate those probabilities? Well, what does it mean to have a probability on A conditional on B? That means that we know for sure that event B happened, and now we want to estimate not really probability of A, but probability of both A and B. So probability of A given B, probability of A given that B happened, is probability of both A and B divided by probability of B. Why do we divide by probability of B? Well, because if probability of B was P and we know that it happened, now probability of after that we think of probability of B as being 1. So whatever probability of B went into calculation of probability of A and B, we need to divide by the probability of B to say, yeah, it's happened for sure. It went from being P to, in our eyes, looking like it's 1. And by the way, in this case, we could always assume that probability of B is greater than 0, because otherwise B would never happen, and we just say B happened for sure. So let's do a little bear puzzle with conditional probabilities. The numbers here are pretty approximate. I was trying to dig out more current numbers, but they're not that easy to come by. So suppose that there are 9,000 black bears and 10,000 polar bears in the province of Newfoundland. And moreover, let's say that all the polar bears live in Labrador rather than on an island, and 2,000 out of 9,000 of black bears are also in Labrador. So 7,000 black bears and no polar bears live on an island, and all polar bears and 2,000 black bears are in Labrador. So let A be an event that bear is a polar bear, and let B be an event that the bear is in Labrador rather than on the island. If you just read about somewhere in an NL in our province encounter with a bear, what's the chance that it's a polar bear? Well, let's say it's the number of total bears in the province, it's the number of polar bears over total number of bears in the province. All bears are equally likely, and we get probability 1/10 that a random bear in the province is a polar bear. With the probability that a random bear in the province is in Labrador, by similar calculation, 3 out of 10 bears in our province live in Labrador. Again, the numbers are probably off, but if you want, you could try to dig out better numbers. Let's just use those for the exercise. So here I made my life easier by saying that all polar bears are in Labrador. Otherwise, this calculation would have been a little bit trickier. But probability of being both a polar bear and in Labrador is still 1/10 because all the polar bears are in Labrador. So probability of being polar bear in Labrador and 1/10, probability of a polar bear on the island is 0. Let's say this is where the more likely to see bears. Let's ignore that you occasionally can see them on the island. So now, what is the probability that the random bear is a polar bear if you know that it's been seen in Labrador? If you see a bear if you know that the bear has been seen on the island, and you know that there are no polar bears on the island, you know for sure it's a black bear, right? So now what the probability of seeing a polar bear if you know that it was in Labrador? Well, it's probability of seeing a polar bear in Labrador divided by probability of a bear being in Labrador, because we already know it's in Labrador. So it will be 1/10 divided by 3/10, which gives you 1/3. And you could calculate it in different ways and just say, well, there are 3,000 bears in Labrador, 1,000 of them is polar bears, so it's 1/3. So you see, you get the same number with two different calculations, but the reason we went through this calculation is just to see how those conditional probabilities work. So let me throw in another definition or another term that we may be using later. So far we looked at an example where that additional information about the event B really told us something about event A. So knowing that there is a goat behind door 3 really told us something about car versus goat behind doors 1 and 2. Or knowing that the bear was seen in Labrador really told us something about the odds that the bear is a polar bear. But it could be that the two events, that knowing event B really tells us nothing about event A. So in this case, we call those events independent. So probability of A by itself is the same as probability of A given B. And another way of stating it, if the two events are independent, then probability of both of them happening is just, according to the product rule, probability of the first times the probability of the second. And again, you could generalize it to more than two events, and there are different conditions, different ways you could talk about it, when two events are pairwise independent or mutually independent. So what are examples of independent events? Say I throw a fair coin, and I'm sure it's a fair coin, and I get the heads. Then I throw it again. Would knowing that it came up heads the previous time give me any information about what I'm going to see next time? Well, if it's a fair coin, it really shouldn't. It still may come up heads as probability 1/2, and it may come up tails as probability 1/2. So those are independent. Or if I throw the two dice, the probability, and I see that the first one got a 1 on it, does it tell me much about what the second one would be? Not really, because if those are fair dice, on the first die you're going to see 1, 2, 3, 4, 5, 6 with equal probability, and on the second die you're going to see 1, 2, 3, 4, 5, 6 with equal probability. And knowing that the first came up 1 tells us nothing about the second.